someone else who could better talk about the combination maybe and also the different technologies of AI and quantum computing and how they shape the digital landscape than Professor Dr. Sabina Jeschke. Your stage.
Ladies and gentlemen, very happy to be here with you today. And I would like to talk about two of my favorite topics, which is artificial intelligence. I'm doing that since about 20 years or so, and the topic of quantum computing, where I have been digging in about 2015. Let me give you just a very brief introduction. Why is it so important to consider both sides of these medals, so to say? We are in a fourth industrial revolution. If you shorten the first industrial revolution to just one word, what would it be? Dampfmaschine, steam engine. If you shorten the fourth industrial revolution just to one phrase, what would that be? It's AI. This fourth industrial revolution is a breakthrough of artificial intelligence. It's a revolution where technological things get intelligent. And what we face today is more or less the algorithmical-driven phase, and we have seen this in Hans' talk. It's about reinforcement learning, deep learning, Q-learning, R-learning, supervised learning, and whatever learning. And we are in the algorithm-driven phase. But we will see that there are at least two other technologies which will skyrocket artificial intelligence on the next levels. One is connectivity, 5G, 6G. And this is because in these protocols, the latency time is so short that consider an autonomous car. Where do you put the computer right now with 4G? In the car. Where would you put the computer with 5G, 6G? In some kind of a cloud, because the latency is so short that it's much better to use a much more advanced machine. In the car, you always have limitations to space, to energy consumption, heat, and so on. So in particular in AI for autonomous systems, this second phase, which is going to break through now, 5G is around, 6G is 2028 about. This will happen now, and then there is HPC, quantum computing, which again brings AI to a next level, and this is my talk for today. And I have kind of 4 chapters. I first would like to get off some wrong assumptions around quantum computing. And then I would like to, from a helicopter perspective, show you, I mean, we already have a lot of computational power, right? So why do I need that? I mean, what's really changing? And then from there, I would like to show you examples. And finally, I would like to couple the topic of quantum computing with sustainability and the climate change. So this will be my outro. I don't have to give a summary at the end. Wrong assumptions, number 1. Oh, I have so many other things to do, I can't care about quantum computing because it's a very long way to go. The quantum age is very far away. You always hear that if you do consulting in this field, as I do. Well, look at these numbers. By 2025, we will see the deep temperature quantum computing stack breaking through on an industrial scale. And 2028, it's the room temperature systems you don't have to cool. So if you consider, I mean, take in particular German industries, how long it has been taking us to understand, accept, and integrate AI, blockchain, and a lot of other technologies. Now we have 2 years to go. Okay, start today. Second wrong assumption, I'm just talking about the left example today because I have been a board member for Deutsche Bahn a couple of years. I don't need quantum computing because you only need it if you do medical research, protein folding, or climate investigations or something like that. Well, this is wrong again. Take Deutsche Bahn. Consider only the tracks, the stations, and the trains. Ignore maintenance, ignore people, ignore everything else. Just trains, tracks, and stations. Write a simulation and come up with a schedule. Computational time would be about 2 or 3 weeks. Which means that this is nice to have, and you can use it to understand, to do analytics, understand about problems, and then come up with a better schedule for next year. But you cannot use it to steer your system in real time. But this is what you need. We have about like 3-4 disturbances per minute. Train is leaving a station a minute too late because of too many people. A group of animals is running on the tracks, we have to stop, and so on and so forth. So it's a very basic question to have more high-performance computing than we have today. It's not only for special applications. Third, I cannot do quantum computing because there are no quantum computers today. Well, this is wrong once again. So first of all, you can prepare your organization, hire the right people, integrate yourself into ecosystems, find out about the best use cases. Perhaps you have some governance problems. For example, bringing all the data together because you want them to use them integratedly. So on the organizational side, there's a lot of stuff to do. But you also can already use certain quantum computers, in particular the annealers. It's kind of an in-between technology. Or you can go for quantum-inspired algorithms, which basically means that you program in a way you would do it for a quantum computer. Since it's not around, you use traditional computers, but later on you just flip the handle. And myth number 4 is, I think I skipped this from my slides, but myth number 4 has been, it's too expensive. Well, now, whenever new technology breaks through, it's kind of expensive. But the first quantum computers will be deep temperature quantum computing. It will be in clouds. You will not buy it. You will not own it. You will have a license for it. And by that, it's getting affordable. And then later on, the more of these computers are showing up, you will not face a problem any longer. So now, what is happening when quantum computing breaks through? This is a bit more philosophical slide, perhaps for the only one. So there have been certain incidents in the development of hardware technology for computer science, which we had a evolutionary development of hardware over the last 70 or so years, but at certain points in time, there was something more. And this was when we freed the computers from the traditional computer centers and came up with a PC. From the physics inside, it was not a big difference, it was just smaller. But before, the computers were just used by a very small group of people, some researchers, some other people, highly educated. And then by having a PC for everybody, we opened up for all people, for diversity, for all branches, for all applications. And we got a revolution within the digitalization without changing very much about the hardware. It was just that we changed the access. So it was kind of a freedom to give people freedom to use it, or give the computers the freedom to be used by anybody. This happened later on with the mobile internet once again. Now it's not about people, but so far, computers have been mainly stationary. Now with the mobile internet, you could have the computers anywhere, everywhere. So we built in a lot of computers into tracks to understand where our trains are, for example. So again, this was a degree of freedom, and now it's more geographically. And what's happening now is there's so much limitations today, things you would like to compute but cannot. With quantum computing, of course, you cannot do everything, and in particular not in the first years. But in general, you will see that it's really opening up what you can do. And this is perhaps my one, but next slide. One more point before I come to that. Moore's law is coming to its end. It might be 2025, it might be 2030, because perhaps we come up with some, tricks. But in general, because of the limitation of the miniaturization, it's coming to its end. We are so much used to Moore's law. If I buy a mobile phone now, I will buy one after 2 years, I expect it to be different, to be better, not only in terms of computational power, but also in terms of computational power. So we are all so much used to this Moore's law. Computers are just getting better somehow, that if this is no longer the case, it feels like being frozen in the innovation of computer science. So it's really good that quantum computing is showing up now by 2025, and it will not only kind of be a successor of Moore's law, it will be more like an explosion in at least 4 fields. We will be capable, number one, of doing totally new things where I could have written the simulation for it, but I would know that to execute it, it would take 20,000 years. By then I would be dead and the computer would be broken. So in general, I can write the simulation, but in fact, I cannot execute it. These are very, very big models, not simplified models any longer. For the next years, I believe that number 2, number 3 is most important. Go again back to my Deutsche Bahn example. We have the schedule planner now, but we cannot use it in real time by now. With Quantum, we can. And that means that we can use these kind of schedules to really steer the system in real time and trying to, whenever something happens, to bring the system back on schedule as fast as possible. Today, it's done by humans. And of course, I mean, if you have a problem in Hamburg, these humans are very good, but they can only optimize for Hamburg. So whatever they decide, you have no clue what's happening in Passau. Number 3, optimal solutions. Very often, we give a computer for optimization problem a certain amount of time. And then within this time, we take the best solution we came up with. If this is the worst but acceptable solution, this is the optimum. Sometimes we get a solution here, and everything else here is waste, but we don't know about it. So I believe that we will come up with much, much better resource usage by using quantum computers. And then finally, product design. We will have simulations based on physical correct digital twins. We will take the simulation, clone it 1,000 times, speed up the speed, and then run simulations in such a way you can never do it in a real lab. And by that, we will come up with an acceleration of innovations, in particular everywhere, but in particular if it comes to the atomic scale stuff. Chemistry, drugs, design, medicals, and so on. 2 more slides for this chapter. I have been saying that there is a cold world of quantum computing, and there is the other one, the room temperature, and even within, I'm going back, come here, even within these both worlds, there are different approaches how to design this hardware, as you can see from the turquoise bubbles. And then there are different companies who are trying to realize that, and they're doing it in a different way. And this is just kind of a screenshot of, I did that a couple of weeks ago. So what I want to say is, here and also here, it's a zoo. Big companies, small companies, traditional companies, new companies, different technologies, warm, cold, in between. So far, we do not know which kind of technology will be successful. There are certain members of the community which say, well, it will be exactly this one, superfluidity, for example. Others are more open. My personal expectation is that in the future, we will have much more different technologies in the computer center because the different hardwares might be more suited for one or the other problem. So I expect that to a certain degree, we will have not perhaps this kind of zoo, a limited zoo, in the computer centers. So, examples. Whenever I come into a company and we agree that quantum computing is important right now, then the question starts, okay, Sabina, we understand now quantum is important. You can use it kind of for a lot of questions. Where should I start? Good question. And what I always use is this kind of slide saying, yes, perhaps in the future you can use it for kind of everything, but now start with, where are you doing or want to do optimization? Where do you do simulation? Where do you do or want to do AI? Of course, very often these pillars are intertackled because, I mean, you have a simulation with a lot of optimization in between, and then part of the optimization might be AI, and the other one might be traditional mathematical stuff. However, think about optimization, AI, simulation, and now go through the rows, general processes. Do you have, for example, an optimization problem in human resources, like bringing all the locomotive drivers on their locomotives in the morning, something like that? General processes are HR, procurement, finances mainly. This is a very nice point to start because here you can start working together with other companies because very often, I mean, let's say you are Volkswagen, you can work together with BASF. You're not in a competition because you're doing totally different stuff, but the solutions to pick the right people or to bring the right people to the right moment and to the right plans is a very similar one. Specific processes means you have a product. How do you produce it? Can you use quantum computing to optimize your production? This is, for example, true for an automobile company steering their robots. I will see this in a second. And then also for the product itself. Let's say you are a bank, you are coming up with some robo-advisor. Could this robo-advisor perhaps be better if it's using quantum computing? If you go through this 3x3 matrix, you will perhaps not find all the interesting use cases, but I guarantee for 80 to 90%. I show you some. And these examples, I'm not picking them because I found them the best in the world, but because they are already realized, because I want to show you that this is not a science fiction talk. So this is IBM and ExxonMobil. And they had the problem that for the liquid gas, you have a lot of ships, you have these gas fields, you have a lot of harbors, and then you have the silos for the intermediate storage and so on, that they were not happy with their routing concept. When a customer comes and says, I want more or less of the liquid gas, then usually the ship goes to a different gas field, the slot in the harbor is gone, and so on and so forth. There are so many parameters already in this question that they have been using annealers to optimize a solution, annealers in contrast to traditional high-performance computing, and came up with very nice results. It's about a year old, this example here to you. Mathematically spoken, this is quite the same, because these are all variations of a traveling salesman problem. Here you have to repair something stationary, in this case a plane, and then you have to get the right spare parts at the right place, with the right people, with the right specialists, in a certain order, because certain things cannot be done before other things have been done, and so on and so forth. And of course, you don't want to have too much storage, and you don't want to have the specialists there, but you cannot use them because you need them in 5 days. So these kind of simulations can be very, very nicely done. This was with a D-Wave annealer. Next example is actually the finance branch has been starting pretty early with quantum computing, or at least with investigations. They did already the same with high-frequency trading. You might remember a couple of years ago, about 7 or 10 or so. Because, I mean, if you trade shares, then you have a lot of data points considering the business industry, but also other aspects like political data points, weather data points, whatever. And the better you can integrate them into a big simulation, the more precise your result might be concerning where the share is going to go. However, if you take too many of these points, then your computational time is too long and you cannot react fast enough. So in finance, a lot of stuff is going on, using all data points in the world to make a very good prediction for which share is going where, but do it very, very quick. And this example, again, fraud detection using quantum AI, is mathematically spoken the same. Because you cannot avoid to be hacked. The only thing you can try to do is, if you get hacked, to figure out about it as fast as possible, like the immune system of a healthy body, and then isolate the problem as fast as possible. So again, it's a question of analyzing the whole structure of your IT system, figuring out, oops, there's a pattern I don't like, and then close the walls. And it's a question of time. And these are 2 examples I have been borrowing from my colleague Florian Neukert, who is now with Terra Quantum, which is a company on quantum computing. But at this time, he was with Volkswagen, so I'm using this logo. Look at these 4 pictures for a second. And for a human, it's very easy to understand that this is a town. X, Y coordinates are the same. It's just that the weather conditions are changing, and so one is night, one is day, right? For artificial intelligences, this kind of image recognition is very difficult. It can be done, but it takes a time. And because it's so slow, this feature cannot be part of autonomous driving today. But we are using this feature all the time. Oops, I've been here before, is something we use to drive a car. So we cannot have this feature, oops, in a car today. But we can using quantum. And this is my last example, again, coming back to AI very straight. Reinforcement learning. Why do we don't use more reinforcement learning? You know this technology. You don't need data, you just let the system try around, hoping for finding its goal. It is a very nice approach, very, very powerful, very flexible, and you don't need data, which is great because of all the privacy issues. The problem with reinforcement sometimes is that if you have a very high parameter space, then the system starts to play yo-yo with its paintbrushes instead of painting the car. because it's allowed to do everything. So reinforcement sometimes has a barrier of being slow at the teaching process. If you can speed it up, and this is what Florian showed, that if you use the speed of quantum systems, you can speed reinforcement algorithms up in such a way that they can be used in production technology, avoiding all this teach-in stuff and so on. Last few minutes. There is a topic nobody talks about. Everybody's just talking about, quantum computing, the new HPC, and so on. But quantum computing will also contribute, it will not solve all the riddle, but it will contribute to sustainability, and this is for 3 reasons. First of all, because we can be much faster in innovating new technologies. Come with an example in a second. Second, because optimization of resources usually means optimization not only in terms of costs or human resource, it also means in terms of something with climate issue, climate impact. And thirdly, we have to consider the energy consumption of quantum computers compared to traditional ones. And for the first example, ESA, European Space Agency, is working on power plants based in the orbit. If you could do that, then, of course, if you put them into the right orbit, that would be signed at any time, 24/7. And that means that you could have green energy, not only by day, but also by night. With about 25 of these fabrics, you could come up with the energy consumption for whole Europe. 25 might sound big, but if you know that we have much more than 100 nuclear power plants, then 25 is close to nothing. So these kind of fabrics, or these kind of big engineering tasks, usually take 4 decades. And now comes what I have been talking before. If you can enhance the innovation speed, coming up with how do I do that, and how do I test it, and how do I whatever, in not 30 years, but 3 years, it could really make a difference. My second example for optimization, always, with optimization, everybody thinks about, okay, I have a truck, or I have a fleet of trucks, and if I shorten traveling salesman, if I shorten the way, then I shorten the diesel consumption. Okay, it's true, but it's boring. This example is much nicer. When you take a plane, you know that the burning of kerosene is not so fantastic for the climate, but actually it's only 1/3 of the problem. About 50% of the problem come from these condensation trails. These are artificial clouds produced by the airplane, and they usually are more warm than the environment, and therefore they heat the environment, and this is exactly what you don't want in the atmosphere. So you can show there's a very nice study from DLR 2 or so years ago showing that if you change the path of the plane in all 3 dimensions, X, Y, and Z, slightly, you can move it in such a way through the atmosphere that the difference in the temperatures is not as much as it is usual, and by that you can reduce the condensation trails. Sometimes you can even reverse the effect, so you can use a plane to cool the atmosphere, which is nice, but it's only a small number of cases it happens. If you do that, you have to recompute the path of the plane by every 30 seconds, and of every plane, and then the interdependence between the different planes. We did a very nice challenge with Deloitte on the AI park, and a lot of startups showed up and showed how you can use quantum computing to solve this riddle. We did estimations. You cannot do it with the traditional hardware around, but you can with quantum. And then my very last slide, to also stay in time. A lot of people believe that quantum computing will take up a lot of energy. This is firstly because high-performance computing always takes up a lot of energy, and second, because they have heard, oops, I have to cool the system down to minus 273 degrees. This is very cold, and this needs, of course, a lot of energy. But the truth is the other way around. The systems themselves, due to the physics, and we're going to have a physics class today, but due to the physics of the system, the computers themselves need only a very, very small amount of energy. Now for, of course, the cold world, the deep temperature systems, you have to cool them, but you have them in specialized environments, a lot of different computers in the same environment, sharing the same laboratories, and so on. So the assumption of the specialists is that it will be about 10% compared to what we need for today. And if it comes to room temperature, there's no cooling. The assumption, we cannot measure it. I mean, this is based on assumptions, physics, talking to the hardware guys. But we assume that we are going down for 2 magnitudes to 1 to 5%. And that's my last sentence. If this happens, the right one, then this changes the game totally. Because right now, even me in my talk, I have been presenting quantum computing as a solution for sophisticated problems. But if this is true, then I would like to switch my iPhone to a Q phone. Not because I really need this kind of computational power in a mobile phone, but because of sustainability reasons, because the energy consumption is so much lower. Let's work on that. Thank you.
Hi. Sabina. So, I have one question.
Yes.
There exists some quantum computer, but not enough, right? And I think for people, it's not tangible enough now. And I know you always say, yes, it's not there now, but you need to start now to have this in like 2 years, for example. The thing is that we need to make these topics a bit more tangible to grab, right? And for example, with AI, there was this happening with ChatGPT. And now for every person who's not tech-related, it's clear, oh, AI is a thing. What could be the ChatGPT happening for quantum computing?
Actually, it might perhaps be the same ChatGPT. You know what I did on the weekend? I told ChatGPT, please program traveling salesman problem, 5 arbitrary cities in C. Okay, it did. And I told him, okay, what do you know about Qiskit? Qiskit is one of the languages for quantum computing. It told me, la 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 la, I can do everything. Okay, program it in Qiskit. And I got the Qiskit code. So perhaps there are 2 barriers. I mean, the first barrier is where is the hardware? Yeah. And the second barrier is you cannot program them in traditional languages. I think the second one we are about to solve. And the first one, if you run your data center on AWS clouds, for example, they already have been starting to offer accessibility to quantum computers around in the world. Of course, the majority of them are kind of babies to toddlers, more to the baby side perhaps, so it's more for proof of concept. But you can start to educate your people, let them try around, figure out about who of your IT guys is really interested in this kind of stuff, so it can be solved.
You also, or I always say, like there are a lot of routes to Rome, always, and the quantum computer finds the fastest and most efficient one, right? Couldn't we also use quantum computing to bring AI to the highest level?
Definitely. I mean, we see that in my last but one example, that this reinforcement topic is really important for Europe, because a lot of newspapers start with something like, industry says I can't do AI because I don't have the data. If you do the reinforcement, you don't need the data. And then people say, well, yeah, but I don't know about reinforcement, and by the way, it's too slow. So in this way, it can be a big, big help. This is just one example. I believe it will be a big help in other areas as well.
I've seen one hand over there. Do we have a microphone, maybe? Yeah, 1 second. Of course we have one. And in the online audience, please also dare to question something. So, who is there?
Hello.
Hi.
Hi.
My name is Joanna Bryson. Thank you for your talk. I have 2 questions. I admit they'll be challenging because the parts I just liked, I don't have questions about. One wasn't really yours, but you mentioned it. I'm terrified of the idea of real-time control of automobiles being done over 5G, because what if somebody disrupts it, if there's a cyber attack? So, and I think this sort of relates to your talk, because that's, I suppose, one of the things you hope quantum will be doing is providing some of those servers. And then secondly, the claims you made on the final slides about what's going on with power, I admit I haven't kept up the last few years, but the last I knew, people were saying that the power usages of quantum are so extreme that only, like, again, security is going to be able to afford it. So what are the current empirical numbers for the power usage?
Yeah.
And when do you see these kinds of returns that you're talking about happening?
Okay, start with the second question. So I don't have a study right now, but working on it actually, and these are kind of pre-results from a lot of communication I had with people from different of the companies. So this is the best estimation I can give you right now. For the first question, the real-time question of autonomous cars. So first of all, if we take, for example, full breakage system, then it's very, very important that this reaction is as fast as possible, obviously. So all concepts like having a human in the loop or something like that would not work in such a situation. So basically we come down to the fact, do we want to have autonomous cars or not? If we want them, then they have to be as secure as possible. And the architecture for that will be to have kind of a little brain within the car, which is capable of, oops, there is a whatever barrier I have to break. And then you have to have the big brain in the cloud. And usually you will compute in the cloud, but when the connection is not there, or when there is a kind of, this system says A, but this system says C, then, okay, start again, something like that. So this will be the solution for that, I believe.
Another short question, maybe. Yeah? Was that a hand? Here, yeah, in the second row. Was there a hand? No. Okay, no, that's fine. Okay, so you're still here, Sabina? We would like to have a short bio break now, but please be there in time, 2:15. And there we will talk about whether Germany can be a technology leader and how. So this is interesting and important for everyone. And thank you. A big applause for Sabina.
Thank you.
Come.